Cool. Hi, everyone. Take a seat. Let's dive right in, I guess. I hope everybody had lunch, right? Everybody's still awake? More or less, we'll see. OK. So generally, who uses databases? I guess everybody, right? Good. Who uses search already? Full text search. That's also nearly everybody. Very good. For those of you who are kind of newer to search and databases, I always compare search and databases with this picture. And I always say this side here, that is the database. This side here is the full text search. Databases are very much about this black and white, where you store something and then you can retrieve direct hits. Yes, you can do something like a like search, but that's normally not very performant and not what databases are really built for, whereas search, while this is not really the reality, it's more about these shades of gray, and you're interested in concepts. So you might be interested in like, oh, I search for pullover, but I might be interested in hoodies as well. And I don't care about singular or plural. I'm more interested in the concept. So that's what search is generally about. And probably a lot of you are already using Elasticsearch or have at least heard of Elasticsearch. If you're searching on any of these sites behind the search box, there is Elasticsearch doing the search for you. Though, if you complain that any of the searches on these sites are not good, I will always blame the implementation and not our system for that. So hopefully the search is good there, and I will show you how to build some things with search. And well, like I've already said in the introduction, I talk about that because, well, I work for Elastic, the company behind the product, and my official job title is developer advocate, but yeah, I always like the avocado better, and nobody knows what it is. And you can also test, like, if you print the badges at conferences, if they do UTF-8 correctly with that. So yeah. Here, unfortunately, I had to write it by hand, so I couldn't test it out. OK, so why is search different than databases? The first thing is you do more work or you do different things when you store something. So behind the scenes, there is Apache Lucene. There's the library that is storing everything on disk. And sometimes people are confused and ask, like, what is the database behind Elasticsearch? There is no database. It's really just Apache Lucene, the library, that is storing everything on disk. And that's all there is. And then Elasticsearch around it is basically the shell or wrapper, which provides the REST API, the query DSL that we'll look into shortly. It does things like sharding and replication. But the actual search and storage is Apache Lucene. And even if you're using another system built on top of Lucene, you will feel very familiar because, well, in the end, like the search features come down to Lucene mostly. So what is the quote in Star Wars when he's making that hand movement? Who remembers? Exactly. These are not the droids you're looking for. So we'll take that as our example sentence to see what search does with that sentence. So these are not the droids you're looking for. The first thing you normally do is you throw out the formatting. So you see we have this emphasis tag there. Nobody would normally search for this emphasis tag. Nobody cares about the formatting. So we just strip it out. Since this is HTML, we have an HTML strip filter, and that will just kick out any formatting or highlighting that you have in there. Next up, what you do is you tokenize. Tokenizing in Western languages is pretty simple. It's basically splitting up on white spaces and punctuation marks. If you have Asian languages, like Japanese, Chinese, stuff is much more complicated. But I have no idea how these languages work, so we'll just skip over that and we'll stick to Western languages. So as you can see, I've added a bit more space between the words, and this is basically where we have broken up our sentence into these tokens, and it is now tokenized. And from now on, we will only operate on these tokens. The next step then is to lowercase everything, because normally you don't really care about upper and lowercase. And if I search on Google, for example, I never type uppercases. I always type my search in lowercases, and I expect it just to find the right things. And while this is not always exactly true, there might be the difference between an us and the capital US for the country. In a lot of cases, you don't really care about upper and lower cases, so you might just lowercase everything, and then you need to just search for the lowercase things, and you never need to care about upper and lowercasing in the future again. Next, after lowercasing, we remove the so-called stop words. So you can see these are not there. Those are all very common words, and they appear in almost every sentence that you have, and they carry very little meaning. That's why we just strip them out, because it would just bloat your index, and you would not find more relevant stuff by them, because these words are everywhere anyway. So we will strip out these stop words, and you're left with droids you looking. And then we stem these 3 tokens, the 3 remaining tokens. And then you stem them down. Stemming is basically getting to the word root. Because you don't care if it's droid or droids in the singular or plural. You don't care about if it looks, looking. You just care about the concept to look. So we stem that down to droid, you, look. That's simple enough. If you want to try that out actually yourself, so we have our own cloud service where you can just sign up and use everything, where you get this login form like that. Or you could use Docker, because everybody has to use Docker nowadays. The minimal Docker setup that you could use is something like this. You just need to replace the Elasticsearch version, which whatever the current version is, and then you get Elasticsearch. And I'll also use Kibana to run some queries, because I'll show you in a moment why this is more convenient. So what you can do is, instead of storing stuff right away, you can just simulate. And we'll do that with the _analyze endpoint, which looks something like this. And to make this more concrete, so if you've never seen it, this is Kibana. And this is the so-called console. And this is the same as doing a curl xget localhost 9200/. But this console, you can see it has syntax highlighting. It will do auto-completion for us. And it can store as many commands as you want. So we have a lot of sample queries here. It's just a bit easier to interact with it. It will also show you if you have some typo somewhere. It will show you that there is something wrong. For example, here, there's something missing. So it will warn you that you need to fix something. We have the current version of Elasticsearch running, which is 6.5.1. And now here with that query, we're just simulating. So if I run that, you can see this is what I've promised you before, like droid, you, look. Because, well, it's an English sentence, we're using the English analyzer, and it figures out what to do. And besides figuring out the tokens, it also has some other helpful things here. First off, we have the position. Are we starting counting at 0 or 1? 0. Like every proper system should start counting at 0. So these are not there, and then position forward, so we start counting it at 0. And you can also see a start and an end offset. That is very helpful, for example, if you want to highlight a hit. If you have a very long text and you want to show this is where your search term is appearing. And then we don't need to parse the entire sentence again, but we just have these positions basically, and we know, okay, this is the start, this is the end, and then you just wrap it, for example, in some emphasis tag or whatever you want. You could customize that. And then you can see very efficiently where is your hit. So that is what you're extracting here. You could also define like a full pipeline. That is what we have here, where we say, okay, we do the HTML strip, we use the standard tokenizer, you lowercase, you remove the stop words, and you stem with the snowball stemmer. And then we have this sentence with the emphasis, and it gives you exactly the same result. But you could totally customize that. So for example, if you say, for your use case, lowercasing doesn't make sense, just leave out the lowercasing step. Or we don't want to stem because stemming doesn't make much sense in our example, leave out the stemming. So returning to our slides, I have all the examples and everything in the slides. I will publish the slides afterwards so you can see and retry everything at home as well. Stop words. Stop words are surprisingly few. I think it's like 33 or 35, I always forget. They're pretty well hidden in the Lucene source code. That's where you can find them. This is the list of stop words. And it was just a coincidence that in our sample sentence there were so many stop words. We'll have other samples afterwards where we have much fewer stop words. But here we just happen to have that many stop words. Should you always use stop words? Any guesses? Yes, no, maybe. Well, it depends. The answer is always it depends. Like if you're a consultant, you will always say it depends and then charge a lot afterwards. But that's also what we will do, that we will also say it depends. Because for lots of use cases, stop words make sense, but not for every use case. For example, what will remain here? Nothing. Those are all stop words. So if you have Shakespeare and have to be or not to be, those would all be stop words, which would be kind of unfortunate, so you would never find that Shakespeare quote again. I think this is the right phrase in Lithuanian, right? More or less? More or less, not really? Okay. But you don't have the movie dubbed anyway, right? So there is no authoritative source for that. So I think I was told in the past that this is more or less the right phrase, I hope. I always have to trust people on that. Any guesses what will happen if you use the Lithuanian analyzer on that? Yeah, no, it doesn't depend. This one doesn't depend. This one will really give you one result. So this is what you get. And I have no real idea what is going on here, but you probably see if this is okay or not okay. These are all the languages that we support. So especially Western languages are well supported. We also have some additional plugins for additional languages, like we'll see those in a moment. And languages are always language specific. So you can see in English, you have this apostrophe S for is, has, or the possessive. That's just stripped out because, well, nobody's searching for that. If in French, you might have the article at the beginning, and then you strip out that, and the accent as well. In German, we have these weird umlauts, and then that special S thing, which looks like a B, capital B, that's just a double S, and that will be stemmed down to those. In other languages, for example, in Swedish, they have an A umlaut, but there it seems to be a totally different letter, because with the Swedish analyzer, the umlaut will remain, because that's what linguists figured out, this is the right thing to do for that language. You can also add more languages. So for example, especially Asian languages, we don't package them by default because it's kind of a large download and a lot to load into memory. So only add those if you really need them. Like Chinese, advanced Japanese, Polish is also a super complicated language. You can add those if you need them. And there's some from the community. For example, for Hebrew, there is only an analyzer from the community. What happens if you use the wrong analyzer on the language? For example, if you use the English analyzer on Lithuanian text. You can see here it tries to apply the English rules, but it doesn't help at all because it's just stemming off the S and the E at the end, because it assumes, well, these are plurals and whatever the rules are. And this is really just rule-based and trying to apply that. So it's kind of stupid. It doesn't really understand what your language is. It's just trying that out. And if you're interested in the Lithuanian stopwords, they're also pretty well hidden somewhere in the source code, but this is where you can find them. What if you don't know the language and you need to figure out what is the language? Right now, Elasticsearch cannot do that for you, but there is a plugin from one of my colleagues in Munich, from Alex. He wrote the ingest language detection. And what it basically does is you create a so-called pipeline where you say, I want to have a field afterwards, and in that field there should be the language. For example, here I can simulate it and I throw that is the German word, and since in German we're stupid and we have all the movies dubbed, this is definitely the right phrase. But if you throw that at that ingest pipeline, it will just tell you at the end, well, this is the sentence, and here you can see here, this is actually German. And then you could actually use the German analyzer to store the text and analyze the text and do the right thing. But you need something to figure out what the language is. Otherwise, Elasticsearch will be confused and cannot do the right thing for you. You could also do stuff like phonetic analyzers, but they give you, let's say, mixed results. It's also like some of them are language dependent. But for example, here, if I look for these are not the droids you're looking for, and I'm interested in what droids might sound like, what the phonetic analyzer gives you is something like this, which I'm not sure how helpful that is. But it tries to make the right sound based on the word. But it's kind of like a hit or miss. It might not work very well for you. Let's take another English example so I can participate here and not stick to Lithuanian phrases. Obi-Wan never told you what happened to your father. What will we get if we run that? Any guesses? Let's actually try that out. Here. Obi-Wan never told you what happened to your father. First off, how many tokens will Obi-Wan be? 1, 2? Well, it depends on the tokenizer, but with the standard tokenizer, you will end up with 2 tokens. So you will get Obi and 1. And then you see never told you what happened your father. So here, there are not that many stopwords in that text, so almost all the tokens are in the output again. Or let's take another example. No, I am your father, which makes sense for Star Wars as well. What will remain here in no, I am your father? Yeah, what you will get is I am your father. Only no is the stop word. And that also shows you one other important thing, that this is not natural language processing. Like no might make a very big difference for a sentence in general, but for Elasticsearch, which only operates on these tokens, it doesn't understand your sentence. It doesn't understand if you're the father or not your father. No or not are just stop words, and they will be removed. It doesn't understand, like, is it positive or negative around father? It will just remove based on tokens. So it's kind of simple, but that makes it also scale very well, because the stupid things are very easy to scale, and they work well for that then. Okay, so we have done those. What is now relevant? Let's look at this. This is the data structure that Elasticsearch stores behind the scenes after analyzing a text. And you can see we have all the tokens that we have extracted. They're stored in alphabetical order. And then we basically have a link. This is a linked list behind the scenes. For every document, you see how many times does that token appear and where. And that allows you a very efficient search, because you basically just, from your search query, you extract your tokens, and then you just look at the right position in the alphabetical order and see, like, in which documents does this appear. And you can also and or connect those very efficiently, because you basically just connect the bit sets. And since you have the position here as well, you can also very easily look for phrases, because basically you say, if you search for droid U, which is a weird phrase, but then you would see that droid appears in document 1 and U appears also in document 1 and 2. But then you could see in document 1 it is at position 4, and at document with the U it's at position 5, so that's a phrase. And you can very efficiently do those phrase searches then by this inverted index structure. And this is what Elasticsearch will always store and create in the background for you. Okay, so one thing that is slightly confusing is we say toIndex to store documents, because it's not just storing but also this full analysis. And dIndex is the thing where we basically store it. It's in a relational world it would be a table, but that is a very bad comparison, so forget that again. But it's kind of the thing where you put related documents. So what we need to do now is we will actually create a so-called index to store everything. And I'm adding 1 or 2 features here as we go along. So first, as my synonym filter, I'm adding some synonyms. And I'm saying father and dad, those are the same. So every time you have father somewhere and you search for dad, you should find the same position. And then we have something where we do a replacement. So here we are doing a replacement. We replace droid by droid and machine, which will basically have the effect that every droid is a machine, but not every machine is a droid, which I think makes sense. So these are the synonyms, and I put them into something I call my synonym filter. And then I create my analyzer, where I do the steps we have seen before, and that as the very last step, we have my synonym filter. So you can see we stem, and after stemming, we will apply those synonym filters. And then we put that into a field my analyzer. So this is called my analyzer, this whole thing. And then I create a mapping where I say I have a document, and then there is one field quote, and that field is of the type text and uses that my analyzer field to store text. And once you do all that JSON, you will actually start to love SQL again, because there you skip all the curly braces. But that's another thing. Since everything has to be JSON here, well, we're sticking to JSON. And I can now just create that index, and it will create that index for me. You could look at that, and you could see here we have, in the documents, we have one field quote, which uses that analyzer. And if you go to the settings, you could see the entire thing where here are the synonyms, and this is what you have set up behind the scenes, basically. And now let's store those 3 documents. And no, this is what I want, this is what I want. And hopefully I have created all 3 now. You could now retrieve everything. And you see, it's just a REST API, so you just do get, post, put, delete, get here to delete to get the document 1. This is actually what you have stored. This is the source. And you have some meta information around it, like which index, which type, which document ID, etc. You could also attach underscore source, and then it would act just like a database, where you just get the field back that you have stored. But that's not really the point of full text search. Yes, you can use it like that, but that's not what you want to do. Let's do some more exciting queries. Here, what is the SQL equivalent of this query? Select star from Star Wars, basically. So you do a query with a match all, so this should give us all 3 documents back. And you can see here, in total we have 3 documents, and then we have our 3 documents that we have stored. Now we could also search for droid. Will this find anything? Yes, it should find something, and you can see here, these are not the droids you're looking for. Will this also find something if I add an S and make this capital? Any guesses? Yes, it will also find something because whenever you search on a specific field, the search term will run through the same pipeline of analysis as your documents that you have stored. So this will also be lowercase and it will be stemmed, so the S will be removed in the end. And if there were any stop words, those would be removed as well. So this is still finding droids because, well, the text you store and the search terms you query, those are running through the same pipeline. What would I find if I search for dad? Do I find anything? Yes, because there is the synonym father and dad. So yes, that will find father, and it's giving you even exactly the same score. We'll get into the score in a few moments, but it should be exactly the same score. So this is 0.72, and if I search for father, you can see it's exactly the same. Since this is a one-to-one synonym, it's just exactly the same thing, and it will find it for you. It could also explain you, if you run a query, why you find that specific document. And for example, here, if you pay attention, we didn't have a document 0, so this is actually the answer if you don't have any documents. But you could just say, this is no match, and this is a document where, okay, this now explains to you why the document 2 matches this specific query. So this is one way to debug why queries are matching or not matching. Okay, so you could do some other searches, but let's skip those because they are not that interesting. What we want to dive into now is, or before we do that, there is one other thing I wanted to show is fuzziness. So if you forget how to spell Obi-Wan and you misspell it as fun, you could just set fuzziness, and you could set that to a specific value, which 1, 2, 3, for example, and that's a Levenstein distance. So it's the number of edits. It's like one letter missing, too much, or different. This is what this would do. And auto basically means depending on how long your query term is, it will set a specific fuzziness value. And you can see here, this is what you get. Even if you misspell one, it will find Obi-Wan. If I search for this Obi-Wan, I misspell both terms and I have a fuzziness of 1. Will I find something or not? Yes, you do, because the fuzziness is on a per token level. And since Obi-Wan is broken up into 2 tokens, you have fuzziness of 1 each. And that is why you will still find Obi-Wan here. And by the way, if you try to do this with a relational database, good luck. Also, this will not be very fast because the leading wildcard, you will not be able to use an index. You will get the full table scan. It's not going to be fun. OK. So one thing that we have not really covered yet was the score, where we had the long number, which the score is basically the quality, like how well does this document match the query that you have sent. And that is the score. So there is this thing that's called TF-IDF, term frequency inverse document frequency, if you search for one term. And it has 3 main components. And the 3 main components are, we have kind of adjusted the calculation behind the scenes slightly, which is called BM25 now. This is best match. This is the 25th iteration of the best match algorithm. Maybe at some point we will have a 28th iteration or whatever. But currently this is the one that Elasticsearch is using. I will show you the difference between TF-IDF and BM25, but it's only like minor adjustments. So what you have is generally the first thing you do is term frequency. If you search for father and one document contains father 3 times, it's more relevant than a document that contains father only once. So you basically take the square root of the number of occurrences, which looks, for the curves, something like this. So here, that axis tells you how many times does your search term appear. And then you have the relevancy on the y-axis. And you can see 5 is more relevant than 1. And the main difference between TF-IDF and BM25 is BM25 just assumes after 5 occurrences, it's not really more relevant. If it's 10 or 15, it doesn't really matter. Whereas TF-IDF was just continuously growing. And like it assumed that 50 is more important than 40, which BM25 pretty much ignores. It flattens out the curve then. Next step is inverse document frequency. This is over all the documents that you have stored. How common is a specific term? And basically the idea is to reward less common terms or kind of dampen very frequent terms. What this looks like is over all your documents, how many times does your token appear? so hundreds of times probably. And then you'd see the relevancy, the fewer times your token appears, like only a couple of times or 100 times, it's more relevant than if it's appearing hundreds of times. It's basically like less frequent things are more valuable because they are rare and they will get a higher relevancy. And the final component is the field length norm, which is also kind of intuitive. If your search term appears in a short field, it's more relevant than if it's in a very long field. So assume you have a headline and the text body, and the headline is very short. If your search term appears there, it's more relevant than if it's in a long text body. It's kind of intuitive. So let's assume we run this query for father, and you could add an explain true to the query, and then it will show you why it or what it calculated in the background. So if you're at some point confused why you get a specific score, you could just add that explain true, and then you would see why what part like was calculated. And you can see the document frequency and the query norm and stuff like that, like how you calculated that in the background. So let's assume we search for father. One document is more relevant than the other document. Why is the first document more relevant than the second one? Yes, the term frequency is the same. Both contain father once. The inverse document frequency is also the same because we're searching for father, and that's the same everywhere. Only the length of the field is different. The first one has a fewer tokens than the other one. And you can also see that the difference is rather minor. All of that applied if you were searching for one term. What happens if you search for multiple terms? This is kind of interesting. Let's assume we're searching for your father. Obviously, the best document would contain your and father. But then the question is, what is more relevant? Documents containing just your, or documents just containing father? And to do that, there is this fancy thing called the vector space model, which looks pretty much like this. This is a bit like made up, but you can see on that axis we have two terms, so we are in the two-dimensional space, and we draw out your, and we assume your is very common. That's why your is not that important, and it has only like a value of 1. Whereas father is very rare, it's much less common, so it's more important, and that has a score of 5. The perfect document would be that vector in the middle, where you see this is pointing to your and father. And then the question is, which documents are more important? The ones only containing father or only your after the ones containing both? And then you basically calculate the angle between the perfect vector and the vector of the terms. And the shorter the angle, the more relevant it is. So here you would see the most relevant documents would contain your and father. And then you would have the documents with father and then the documents with your. And if you have 3 tokens, it would be 3-dimensional, etc. But that's much harder to draw out then. So let's stick to the 2-dimensional model because that's very easy to keep in your head. You also have a so-called coordination factor where you basically say if you search for 3 terms and a document contains only 1, you will punish that document. Whereas if all 3 terms appear, you don't just add the scores, but you divide it 1 divided by, or the number of terms appearing divided by the number of terms you're searching for. So basically reward the more terms are there, you will reward those documents. Then you can put all of that together into the so-called practical scoring function, and we've seen all of those already. So you see the term frequency, the inverse document frequency, you could boost specific fields or terms. The query length norm, you just put all of that together, and then you get the score out of that. You could calculate that in your head, but it's kind of complicated, and Elasticsearch will luckily do that for you. Or actually, Lucene will calculate it. You could also influence that by writing a function score. And for example, the easiest one would be a random score. If you run that, if you search for father, so let's go to, no, this is not where I want to go. This is the one I want. If you run a random score, you can see, depending on how often you run this, the score will just vary, and different documents will be up first. This is, for example, helpful if you have a lot of documents and you want to have some sample, where you want to get 20 sample documents out of a very large text body. Or if you're at a conference and somebody is doing that prize giveaway, that is how we draw the winner normally. We put everybody who is participating into Elasticsearch, and then we basically say, give us the top 1 person, and with a random score, and then we get 1 lucky winner out of that function. And for scoring, there's one other thing. Oftentimes people want to compare like the perfect 100 score versus a 50% score, or they want to put a percentage on the scores. And this is a really bad idea. and it's not working, but people keep trying. So that's why I'm trying to tell everybody not to do that. Even the documentation from Lucene has this very nice quote, like, don't do this, seriously, but people still don't want to believe. So I can show you why. So let's say we analyze this sentence, these are my father's machines. What will remain of that? My father, dad, machine. So you can see here, synonym at work, my father, dad, machine. This is what remains here. So if we store a document like that, and then, so we store that, and then we search for my father machine. Like this contains all the 3 tokens that we have in this one document. So you could assume this is a 100% match, right? Who would agree that this is a 100% match? Good. 1, oh no. No, you should not agree. Because yes, you could say like 2.9, whatever is that is the perfect score, and this is like 100% now. The problem is what happens if you delete that document and then run the same query. Then suddenly you will have a document with the best score of 1.2. And then the question is this now a 43% match, or is this your new 100% match? And it gets even worse if you add another document. This might be slightly made up, but let's assume we add these droids are my father's machines. And here you can see, because of the term frequency, we have father twice, and then droid machine, we have that twice as well. So the score should be higher because the term frequency influences that more. And if you search for that again, then you suddenly have 3 point something, and now suddenly you have a 103% match. So the percentages just don't work. The score is only relevant within one query. Also, don't compare scores between queries, but because that also doesn't work. A score is only relevant within one query. So please don't do that. It's not going to work out well. Performance-wise, people often ask, like, OK, show me how well this is performing, or how much better this is performing than this other system. This is my favorite comic for any performance-related questions. And this is what you get when you benchmark your product against any other product. So don't believe any benchmarks out there. Normally, you find the perfect scenario for your tool, and then this happens. So that's why we don't do any benchmarks with others, because normally it's not really fair, and you will just drown the cat. The other thing is, people often say, like, oh, we have 1 million documents. And it's a bit like, if you remember Austin Powers, Dr. Evil, coming back from the past, when he asks for some ransom, and he asked for $1 million, because in the 60s, this was a lot of money. But nowadays, it's not that much money anymore. And that's pretty much how we feel when people say, like, we have 1 million documents. And we're always like, yes, that's cute. You can totally do that. Elasticsearch will eat it for breakfast. Go crazy with your 1 million documents. We don't really see any problems there. So to wrap up, we have looked at what happens when you store your documents. I think we've seen all of those. We've looked a bit at scoring, what is being done behind the scenes to figure out what is relevant and what is not relevant. And there's one more thing. We have released that yesterday night as a beta. If you don't want to care about the internals so much, we try to bring more solutions out now. So you can tune all of that and do that with Elasticsearch yourself. But we also have a product which tries to take care of that for you. And I'll just quickly try to demo that. And well, it's a demo that came out yesterday night. So you basically have a thing that you can run locally. You can see it's running here on my local machine. And basically, let's say I create one data set for test. And let's say this is English. Then you create this so-called engine. Create the engine. No. This is what happens with demos. Ah, it locked me out. Let me log in again. So this is what this looks like. Let's say we have test. We create the test engine. And then you could either paste JSON or upload a document. I will upload a document, and the document looks like this. So we have, it's only 2 JSON documents, but you have just a JSON document. You have description, states, title, various fields. So basically, we will just upload a JSON document. There's, of course, also an API where you can throw in more documents, but this is easier, so you can see it detected 2 documents and 10 fields. And then it will tell you, OK, we didn't run many queries yet, but you could look, for example, of what data, what data do you have? So you can either look at the fields or the documents. These are the two documents that you have, and you could unfold those here, or you could also see the schema. The nice thing here is that you can influence the schema afterwards. So for example, you could say, this is a number, this is also a number, this is a date, and then you have a location, that's a geopoint, and then you have acres, this is also a number. And then you could just confirm the types, and then it would apply that and index your documents the right way. And that you could run a query tester. And for example, here in your documents, let's take a quick look again. For example, what might be an interesting query is I have treeless, and I have also trees. So for example, you could test what happens if I search for tree. And then you can see this document here ranks 0.76, and this is 007, but you didn't need to configure anything how to store that or how to search for parts of the words. This is taking care of that for you. You could also add synonyms through a UI, you could curate specific queries, or you could do some relevance tuning where you say, for example, the World Heritage Site is much more important, this field should have a weight of 5, for example. And you can just click that together, and it will also keep track of what you have searched for or what your users have searched for, what results they have been getting, and what results they have been clicking on then. So you can keep track of what people are doing. Otherwise, you would always need to build that yourself. But you can totally do this. This is just using Elasticsearch under the hood, but we have kind of like more wrapper around it. And this is also a free product, so you can just run that for free on your site if you don't want to build that yourself. I have linked to the blog post, so if you want to give it a quick try, this is exactly what I've shown you today. It's a beta, it came out yesterday night, so yeah, tell us about any bugs you encounter. And with that, I still think we have some stickers left over there, so if you're quick, you might get some. Do we have any questions in the audience?